Hey guys, Mr. Smith here. And in today's video lesson, our first lesson of our fourth unit on trigonometry, we're going to be talking about radian measure. So let's get started. I'm wearing my coat today because it's very cold in my school. The heaters are not on yet, and they will not be on for the foreseeable future. And I have some huge windows in my little office space here, so it is cold. But that won't stop me from trying to do my best here. So let's get started. Um, did you know there are different ways to measure angles than just degrees? Um, if you're curious about where degrees got their origin, the 360 degrees for one revolution is curiously close to 365 days in a year. And that's actually where degrees originated. So ancient astronomers were kind of observing patterns in the sky and noticed that the stars in the sky would rise and set in a single night, and around the North Star, they kind of moved. And if they, as they tracked it over a course of a whole year, they would complete one circle. And hence, about 360 days to do one revolution. They kind of 365 days, 360 degrees, kind of made the connection there. And yeah, they broke the sky up into 360ths, and we still kind of use this idea today for 360 degrees as a full revolution. Another way to measure angles is in gradients. So hopefully this never happened to you, but I've seen it's happened to some of my students before where they go back in back in grade 10, they're learning about trigonometry. We're using SOHCAHTOA, and all the angles are in degrees. And instead of working in degree mode on their calculator, they have their calculators stuck in one of two other modes: grad mode or rad mode. And actually, grad mode is just refers to gradients. It's another way of measuring angles. And this measure originated during the French Revolution, and was a way to kind of standardize angles to like the metric system. You know, the metric system is like powers of 10. So what gradients tried to do was take a right angle, which in degrees is 90 degrees, and break a right angle into hundreds. So instead of a right angle being 90 degrees, they said it was a right angle would be 100 of these gons. And so one complete revolution would be 400 gons. And one way this was useful is that two angles would always be perpendicular with each other. If one angle was if you just add 100. So if you had 17 degrees and you wanted to know what angle was at a right angle to that, you just add 100, so 117 degrees. So I mean that does make things easier in one sense, but I'll tell you, I've never used gradients in my life, and I have a master's in mathematics from Waterloo, and I've never talked to anybody who used gradients either. They might be out there. There might be some kind of engineering thing, but yeah, we don't use gradients that much in modern times. However, we do use the final one. And this final mode, rad mode, doesn't stand for rad actually. It stands for radians and radian measure. And today we're going to learn about how to measure angles in radians. So here we go. Yeah, as I said, today we're talking about radians. And so back in your grade 10 course, you guys would have talked about what you call a curved segment on a circle that kind of joins two parts in a circle. And we called this an arc. So measuring angles in radians, how you do that, it's basically a ratio of how long the arc is compared to how long the radius is. So if you have a very tiny little arc, it's going to be a very tiny ratio of arc length over radius, and you'll have a small angle. And then if you have a larger arc around the circle, obviously that'll be a bigger ratio and you'll have a bigger angle. The radian measure of an angle theta is defined this way. It is a, excuse me, it's a ratio. It's a ratio of two things. It's the length of the arc. And the length of the arc we refer to as A divided by, I should say too, it's the length of the arc formed by the angle theta. I definitely should include that. Formed by angle theta divided by the radius of the circle. Of the circle, and we use R for that. So I'll just bring up a different colored pen here and get this down. So the measure of an angle in radians is this ratio of the arc length formed by the angle divided by the radius of the circle. And to get our first kind of idea of how degrees and radians are related to each other, let's think about one complete revolution of a circle. And in the case like this, for a whole revolution of the circle, that arc length is actually just the circumference of the circle itself. So for one complete revolution, the angle theta is the arc length divided by the radius, which in this case is the circumference, 2 pi r, divided by the radius, which gives you 2 pi. We say 2 pi radians, or 2 pi. Often we use short form. We use 2 pi rad or 2 pi rad if you're reading it. One complete revolution of a circle measures 2 pi radians. Now, you actually may have seen this before as an exercise in maybe one of your grade 9 math classes or grade 8 math classes. It turns out for any circle at all, if you maybe take a piece of string and form the radius of the circle, if you take that piece of string and kind of lay it out around the outside of the circle, it's going to go around half the circle exactly pi times. Half circle equals pi of these radii. So maybe you did that in your, perhaps you did that in your grade 9 course, but that's true for any circle. And what we just showed is that for a whole circle, you can, it would be 2 pi, or 6.28 of those radians. So we've got our first kind of connection, 360 degrees is equal to 2 pi radians. So that's like the starting point for our work today on converting back and forth between degrees and radians. Here's our starting point. Full revolution of a circle is 360 degrees. Full revolution of a circle is 2 pi radians. Why 2 pi? Because if you picked up a radius of the circle, it'll go around the circle exactly 2 pi times, about 6.28 times. Let's develop a method to go from radians to degrees, and then from degrees to radians, and then we'll just start getting some practice doing a bunch of conversions. So how do we go from radians to degrees? So we'll make use of the fact that we just talked about, the 2 pi radians, so I'll just write down 2 pi rad, is equal to 360 degrees. Well, what does that make 1 radian equal to? Well, if we just divide both sides by 2 pi, we get that 1 radian is 360 divided by 2 pi degrees. And we just divided by 2 pi here. And that's it. We can clean that up a little bit, actually. 1 radian, 360 divided by 2 is 180. 1 radian is 180 divided by pi degrees. And there we just simplified. So to make just a little conclusion there, I got a lot of space here, but what we have shown is that 1 radian is exactly 180 divided by pi degrees, Or if you want to know what that is kind of approximately in degrees, you can do 180 divided by pi. 180 divided by pi, about 57.3 degrees, just to give you kind of a reference point. So this is how we can determine any angle measure that's in radians. We can convert back to our old friend degrees using this conversion factor that 1 radian is 180 divided by pi. Let's develop a rule for converting from degrees to radians. So we'll just kind of do this the same thing backwards. So for degrees to radians, we know that 360 degrees is equal to 2 pi radians. So what is 1 degree equal to? Well, 1 degree would then be 2 pi divided by 360 radians. And here we just divided by, I'll just use a star like I did the last time. Yeah, we just divided by 360. Divided by 360. And then we just simplified that. 2 pi over 360, we can simplify just to pi over 180. 1 degree is pi divided by 180 radians. And here we just simplified. So our conclusion there, 1 degree is pi over 180 radians, or about, if you're curious about what that is, that's pretty small. Pi divided by 180. Let's see how small. Why did I lose my pi button all of a sudden? That's okay. I'll use 3.14159 divided by 180. Okay, so that's not a lot of radians. It's about 0.0175 radians. So pretty tiny in terms of radians. So yeah, that's how we can convert from degrees to radians. So now that we have these kind of conversion factors, let's just get some practice stating some angles in radians and stating some angles that are radians in degrees. We'll start off with some simple ones. So you might have heard me actually read out those angles in terms of rad. So instead of saying 2 pi radians, I might have said 2 pi rad. Often when we're writing the angle in radians, we actually just drop the rad and just write the angle. So for the example there, when you see an angle with a degree symbol, we understand it's in degrees. When you see an angle with no symbol, the interpretation there is like, oh, they're giving me the angle in radians. It's not 6.28 degrees. If it was degrees, it would say degrees. 6.28 is measured in radians. And finally, a lot of times we actually state exact angles in radians, and we write them in terms of pi. So here's some examples. So 360 degrees. We already understand that's equal to 2 pi radians. And we just write 2 pi. With no units, we understand that to be in radians. 180 degrees in radians, pi radians. 90 degrees in radians, pi over 2. 30 degrees in radians. Well, 30 is 1/6 of 180. 30 degrees, pi over 6 radians. And so on and so forth. I mean, I'll do one more. 10 degrees, that's 1/18 of 180. So 10 degrees we can write as pi divided by 18. So often when we can, we like to write angles and radians in terms of multiples of pi. And there are just some examples for you guys. All right, let's do a few more examples. It's some new terminology. It's a new way of measuring angles. Let's get used to this a bit more. All right, so we actually kind of talked through the 30 degrees, but let's actually do an example here. So the key idea, if you want to go from degrees to radians, think back to our conversion. You want to go from degrees to radians. Here we go. Every 1 degree was pi over 180 radians. So we're going to use that. I'm just going to get this down as a key idea here. So to convert degrees to radians, degrees has two e's. What we're going to do is we're going to multiply by pi over 180. Okay, and the reason why pi over 180 we established before. So let's try this out. So 30 degrees, to get in radians, we do 30 and we multiply by pi over 180. And we simplify. 30 over 180, we can simplify to 1/6. And so we write that. Instead of writing 1/6 pi, we usually write this. We write pi over 6. And there we go. Degrees to radians, multiply by pi over 180. And we've got it. Approximately how many radians is this? So we'll do pi divided by 6. Guys, I seriously lost my pi button. Where did my pi button go? It's crazy. 3.14159 divided by 6. Okay, so about 0.52 radians. And maybe since I have some space on this slide, I can talk about what this means. So say we had a circle, copy this down or not, it's okay. It's your notes. What does 30 degrees mean? So if I kind of had this wedge that's formed by a 30-degree angle, what that means is if I were to look at the length of this arc right here, this arc length would be equal to about 52% or 0.52 times the radius. So trying to make that connection between radians and the radius of a circle. So yeah, about 0.52 radians. But again, we often leave, when we're working with angles and radians, we'll often leave them in exact form as a multiple of pi. Here it's 30 degrees is 1/6 times pi. All right, let's work backwards. So here are some angle measures in radians, one in exact form and one in approximate form. And let's find out what they are in degrees. So the key idea, very similar to the previous one. To convert degrees to radians, we multiply by pi over 180. To do radians to degrees, we flip that, 180 over pi. So to convert radians to degrees, multiply by 180 over pi. And I'll actually put 180 over pi degrees because radians kind of dimensionless, and to get the degrees on there, we'll multiply by 180 over pi degrees. How's this work? Let's look. So for pi over 4, to get this in degrees, we're going to take pi over 4. We're going to multiply by 180 divided by pi degrees. And you can see here, pi divided by pi divides to 1. 180 divided by 4 is 45. Pi over 4 radians is exactly 45 degrees. And actually, I kind of purposely avoided doing that on this slide here. If 180 degrees is pi, 45 degrees is exactly a fourth of 180. And so 45 degrees, it makes sense. It's exactly pi over 4 radians. Okay, so there we go. And so that was exact. No need to do any rounding. For B, 5.86 radians. Again, no units. You know it's in radians, okay? So we'll take 5.86, multiply by 180 over pi degrees. And we'll have to get, there's no nice canceling here. We just actually have to do 5.86 times 180 divided by pi. And I got to the nearest tenth, 335.8 degrees, approximately. And that makes sense too, guys, right? Remember, for a full circle, that's 2 pi radians, right? Or about 6.28 radians. So 5.86 radians is really close, not quite, it's really close to a full revolution. So the angle in degrees should also be pretty close to a full revolution. And yeah, 335.8 degrees is getting pretty close to 360 degrees. All right, so we've defined what radian measure is. We've compared radians to degrees and showed how to convert back and forth. And now we're just going to do a couple kind of straightforward examples um, uh, before finishing up our lesson for today. All right, so in this particular problem, given an angle in radians, we're going to find an arc length using the definition of radian measure. So Bort is getting on a carousel. So everybody has been on a carousel before, or maybe not actually. Got a diagram of a carousel there. But I'm looking top, if you're looking from the sky down at this carousel, the distance from the center of the carousel to the outside is 9 meters. And what we have in this question, Bort is on his camel at the start. And Bort goes through an angle of 5 pi over 6. Now, this isn't part of the question, but maybe for the sake of drawing this out, what's 5 pi over 6 in degrees? Do you want to maybe pause the video? And I'm going to try to remember to put this in Edpuzzle and ask you, what's 5 pi over 6 degrees, or 5 pi over 6 radians in degrees? I'm just going to play catch up here now. Hopefully you paused the video and gave that a try. So 5 pi over 6 radians, multiply by 180 over pi degrees. Pi over pi divides out. 180 divided by 6 is 30. 5 times 30, this is 150 degrees. So maybe some of you guys figured that out. You know that pi is 180 degrees, pi radians. 5/6 of 180 is 150. So essentially, Bort has gone 150 degrees, or 5 pi over 6 radians. And so now he's somewhere right here on the ride. And what we're asked to find is the length of this arc. Now, this kind of question is possible to do without any knowledge of radians. You can kind of find what ratio of the full circle a Bort traveled by thinking of what percentage of a circle, what ratio of a circle is 150 degrees out of 360. You can do it that way, but we're just going to use the definition of radians. So remember that the angle in radians we defined as the arc length. I'll just write this out. Arc length divided by the radius of the circle. Here, our angle in radians, 5 pi over 6. The arc length of the circle, we're trying to find that. We'll call it A. And the radius of the circle, we know the radius of the circle was 9 meters. So we just have to solve for A. So let's do that. We can multiply up the 9. I'll just do 9 times 5 pi over 6. And we can just do, we get 45 over 6. And if you want to simplify that, you can divide both those by 3. And you get that the arc length is exactly 15 pi over 2 meters. So that is exact. But what's that as to the nearest tenth? like the question asks. We can just do that multiplication and division. Can't believe my pi button. I just can't get over this. Where's my pi button? Oh, guys. Okay. So I was looking for my pi button as one of my orange buttons, but it's not. It's actually a button itself. Pi. Ah, okay. 15 times pi divided by 2. So approximately 23.6 meters. So we can just like tie a ribbon on this question. The camel traveled 23.6 meters in total. So guys, using the definition of radians, you can find arc lengths pretty quickly and efficiently by just using the definition. Let's do one more. So many of you guys taking grade 12 functions have also taken physics and talked about velocity, acceleration, et cetera, et cetera. But I think even if you haven't, everybody understands when something is moving, it has a speed or, loosely speaking, a velocity. But you can have something stationary that's actually spinning very, very, very fast. And I think we all have some experience with that. Like, if you spun a bike wheel really, really fast, it's not very pleasant to actually like touch the wheel, right? So this idea of angular velocity is something that you're going to explore a lot more if you take some physics in university. But angular velocity is just a way of measuring how fast something is spinning round and round and round. One way to measure that is in revolutions per minute, or RPMs, as you might have heard. And so an RPM is how many times in 1 minute your spinning object will make one complete revolution. So here we're looking at a hard disk in a personal computer, and those disks spin very, very fast, 7,200 revolutions every minute. Well, what we're going to find now is, well, how many degrees of revolution happen every second? And then pulling on our new stuff, how many radians are revolved through every second? So let's give this one a go. Part A. I lost my pen. There we go. Yeah, let's do part A. So 720 revolutions. How many degrees is that? So let's find out. So the hard disk rotates how many degrees? So it's 7,200 times. This hard disk rotates 360 degrees. That's a lot of degrees. 7,200 times 360. That is 2,592,000 degrees. Every minute, this hard disk revolves that much. And well, now we can calculate the angular velocity because we have the degrees and we have the seconds. Angular velocity. It's the degrees divided by the seconds. 2,592,000 degrees. We know that happens every minute, which is 60 seconds. And I believe this, since 7,200 works out, divides by 60 nicely, I think this should work out nice. Divide by 60. Yeah. 43,200 degrees per second. So that's pretty fast. Do I have? Yeah, let's do B. I'm going to squeeze B in here in the same way. So we could do B just by converting those degrees into radians. And I might show that as an alternative method in a second. But let's just repeat the process here for radians. So the hard disk rotates. In this case, it's 7,200 revolutions, but every revolution is 2 pi radians. So this is 14,400 pi radians. In 1 minute, I should say. And so the angular velocity, (14,400 pi radians for every 60 seconds. This works out pretty nice too. 14,400 divided by 60. Yep. About 240 pi radians per second. So both are total valid. So the angular velocity of the hard disk, either 43,200 degrees per second or 240 pi radians per second. An alternate way of doing this question would just be to take 43,200 degrees per second and multiply by our conversion factor of, have that backwards, pi over 180. I don't need the brackets either. Yeah, multiply by our conversion factor of pi over 180. And we should get the same thing. If you do 43,200 divided by 180, 240. And this would be radians per second. Pi radians per 180 degrees. The degrees divide out. So you could have got it using a little conversion like that. I missed the pi too. There we go. Pi. I thought B was a bit more helpful though. Okay, so what have we seen today? We've been introduced to this new way of measuring angles, radians. We defined what it was. We made a whole bunch of comparisons between an angle in degrees and what the corresponding angle in radians are. We talked about how often the radian measurement angle is often given an exact form as a multiple of pi. We gave a bunch of examples there. We developed some rules for converting back and forth to degrees to radians, multiplied by pi over 180, to convert from radians to degrees, multiply by 180 over pi degrees, and then did a couple of fairly straightforward calculations, application problems. But that's okay because this is a brand new thing. It's a brand new way of thinking about angles. It's going to take some time to sink in. So that might look like a lot of questions. A lot of these questions in the McGraw-Hill-Ryerson text are like, question one, it's like 6 parts. Convert this angle to this in radians in exact form. And it's just a lot of practice to help you get comfortable converting from degrees to radians and vice versa. So as usual, though, like do as much or as little as you want to. But I would suggest spending some time and making sure you're very, very, very comfortable working with radians. You want to have a really good understanding of how the degrees and radians kind of match up. In our next lesson, we're going to revisit the unit circle and special angles. So in grade 11, you learned that some special angles like 30, 60, 45 degrees, 0 degrees, 90 degrees, and a bunch of multiples of those had exact trigonometric ratios. And you might have memorized them depending on who your teacher was. We're going to revisit the unit circle and we're going to revisit these special angles, but we're going to look at them in terms of radians. And that'll set us up for our final few lessons in the unit. But yeah, guys, until then, please practice. Get really comfortable working with radians so that moving forward, we're in good shape. Hope you guys are staying well. Take care, and we'll see you soon.